Diraj Tao is a company specializing in the production of forged and rolled parts for heavy engineering and machinery, following a rigorous and precise manufacturing process. The process begins with selecting raw materials, with the company maintaining a stock of 30,000 tons of steel, including carbon steels, alloy steels, and stainless steels. These materials are carefully chosen to meet the durability and quality requirements of the final products. After cutting the raw material into precise billets, it is heated to temperatures between 1,150 degrees Celsius and 1,250 degrees Celsius in preparation for forging. Smaller workpieces are forged using steam hammers, while larger components are processed using hydraulic upsetting presses with forces up to 40 meganewton. For parts weighing up to 35 tons, the forging process is handled by mobile hydraulic manipulators and presses capable of lifting up to 50 tons. A significant part of the production process involves the creation of seamless rings, forged and rolled with modern machinery to ensure tight tolerances and near-final shape. These rings are used in applications such as gears, bearings, and other critical mechanical components. After forging, the parts undergo heat treatment in advanced furnaces to improve material properties such as hardness, toughness, and wear resistance. The workpieces are then moved to CNC machining centers, where they undergo precise turning, drilling, and milling. Each product undergoes rigorous quality control tests, including ultrasonic testing, tensile testing, and hardness testing, to ensure they meet the highest standards. Once quality is verified, the products are packaged and shipped according to customer requirements. Diraj Tao's manufacturing process ensures the production of high-quality products used in industries like wind turbines, shipbuilding, energy, and mining, maintaining a strong reputation for reliability, precision, and innovation in forging. By combining traditional forging methods with advanced technologies, the company delivers high-performance components designed to meet the most demanding industry standards. The manufacturing process at LH Group's wheelsets unit begins with the initial inspection and assessment of wheelsets and bogie components. The parts are then disassembled and thoroughly cleaned. Wheels are heated and pressed onto axles using a 400-ton press to ensure a secure fit. Reprofiling is carried out using specialized machinery, followed by dynamic wheel balancing. Non-destructive testing, such as ultrasonic and magnetic particle inspection, is performed to detect potential defects. Bearings are inspected and replaced as necessary. Finally, components are reassembled and undergo final quality checks before being delivered or installed in vehicles. Thai alloy manufacturing showcases a high-tech, efficient production process emphasizing quality and stability. Key steps include tilt casting machines for precision, air leakage and static balancing checks, followed by sandblasting. Rims receive an automatic powder coating and diamond cut finishing. The sputtering chrome machine enhances surface strength. Products undergo rigorous impact resistance tests, meeting TÜV and VIA standards. Each wheel passes intensive visual and appearance control to ensure top-tier aesthetics and performance before delivery. AZ Spa specializes in precision machine tools for crankshafts up to 12.5 meters, with over 3,000 grinders sold in 91 countries, including cylinder and engine block grinders. The bicycle rim manufacturing process begins with a high-grade aluminum alloy, which is rolled into the desired shape. The formed strip is then cut to length and joined at the ends by welding or using inserts. The rim is then heat-treated to increase strength and hardness. CNC machines are used to drill spoke holes and finish the braking surface. The rims undergo rigorous quality checks including static balancing, impact testing, and a final visual inspection, ensuring each rim meets high performance and safety standards before shipping. This time-lapse video documents the entire process of building a custom 16-foot welded aluminum boat, designed and built by Eli McKenty at Elegant Fabricating. Built with precision and attention to detail, this center console boat features a self-draining deck and is powered by a 50-horsepower Honda outboard motor, reaching a top speed of approximately 30 knots. The welding process for the custom 16-foot welded aluminum boat built by Eli McKenty followed a careful, methodical approach to ensure strength, precision, and durability. Working with 5052 marine-grade aluminum, which has excellent weldability, Eli used a combination of MIG, metal inert gas, and TIG, tungsten inert gas, welding techniques depending on the part of the boat. The process begins with surface preparation. All aluminum panels and plates are thoroughly cleaned to remove oxides and contaminants that can cause weak welds. Edges are beveled, or prepared with small clearances to ensure proper weld penetration. Next comes tack welding. The bottom hull panels, side panels, and deck panels are positioned and tack welded together. The tack welds hold the components in place, while allowing for adjustments to maintain alignment and prevent distortion. Once the basic frame is established, the full welding process begins. MIG welding is primarily used for larger structural joints, such as hull seams, bulkheads, and stern connections, because it provides good penetration, is faster, and is suitable for thicker materials, 1/4 and 3/16 plate. MIG welding provides strong, uniform welds that are ideal for heavy structural loads. For thinner sections, such as 1/8 side panels, decks, and consoles, TIG welding is used. TIG provides better control of the heat input, reducing the risk of warping thinner aluminum sheets. It also produces cleaner, neater welds, especially in highly visible or detailed areas. During the welding process, Eli works in a controlled sequence, alternating sides and moving methodically across the structure to minimize heat buildup and distortion. Backstepping techniques and skip weld patterns are used to help distribute heat evenly and maintain dimensional accuracy. Critical joints, such as the self-draining deck and stern seams, are thoroughly inspected and sometimes double welded for added strength and water resistance. After the build is complete, the boat is powered by a 50-horsepower Honda engine, known for its reliability and fuel efficiency. Sea trials have shown excellent performance. The boat easily reaches 30 knots, providing smooth handling and dry, comfortable travel even at high speeds. And finally taken out for testing. The Rigid 238P powered soil pipe cutter is a compact, lightweight, and powerful tool designed for efficient pipe cutting in tight spaces. Weighing only 13.5 pounds and measuring 11.5 inches in length, it offers excellent maneuverability and access to overhead or confined pipe locations. The 238P can be operated using either a 1/2-inch impact driver or a manual ratchet, providing flexibility on the job. It features low-profile cutter wheels, a removable handle. The aerospace landing gear part is first cut using Mastercam with an OptiRest strategy, utilizing a 2 inches fly cutter and a 1/2 depth of cut with a .400 step over. After roughing the first side, the part is moved to the Centroid A560 machine for the second side roughing. It is then set up for 5-axis finishing operations, where precise cuts are made to achieve the desired finish and dimensions. The production process at SMS Group's copper plants starts with ore or scrap processing, followed by smelting and refining to remove impurities. The purified copper is then cast into semi-finished products such as slabs, billets, or coils. Subsequent rolling, pressing, and heat treatment stages ensure the desired mechanical properties and surface quality. Advanced automation and process control technologies optimize efficiency, reduce energy consumption, and minimize emissions, delivering high-performance, sustainable, non-ferrous metal solutions. Daily machining and drilling of Vatak gate valve DN700 in full stainless steel SS316 involves precise cutting, shaping, and drilling of valve components. The GMWE Motors stator production line features advanced technologies for high-efficiency manufacturing. It includes a human-centered operation with servo-controlled paper feeding, ensuring smooth material handling between stations. The system offers parallel winding capabilities for up to 8 wires and a servo-controlled wire clamping system for precise wire placement. It incorporates a turnable setup with 2 working stations and enables 3-phase insertion in one go. A servo-controlled insertion mechanism ensures accuracy, while the vertical flip feeding accommodates medium to large stators. The line also includes separated dimension forming for consistent collet shapes and an easy-to-operate design. The production process is fully servo-controlled, with 3D forming design and pick-and-place functions, ensuring quick delivery and optimal results with double-ends lacing for larger stators. The MUge circle segment and trochoidal milling strategies showcase significant advancements in machining efficiency. In this demonstration, MUge end mills are used on P20 tool steel, comparing traditional and modern milling techniques. The circle segment strategy is employed for finishing a surface, achieving a 90% reduction in cycle time and providing an improved surface finish compared to a standard ball-end mill. For pocket roughing, the multi-cut roughing strategy is tested alongside the jet-cut trochoidal strategy, which incorporates a chip breaker for enhanced performance. The jet-cut trochoidal method is also used for finishing the pockets. Additionally, roughing is performed with a top-cut VAR, with and without radial chip thinning. This demo was carried out on a Herco VMX30 machine using Mastercam 2017 software, demonstrating the efficiency and precision of the new milling strategies. The 3D sand printing process for engine blocks starts with engineers designing a digital model of the part using CAD software. The model is then converted into a 3D sand mold using a specialized printer, which combines sand and binder. The printed mold is sent to the foundry where it is inspected for quality. In the foundry, metal is melted and poured into the mold, forming the engine block. After cooling and solidifying, the sand mold is removed, revealing the cast engine block. The final part undergoes testing for performance and durability before being used in production. This method offers rapid prototyping for efficient evaluation. 4-axis CNC milling with an automatic tool changer enhances machining efficiency by allowing multiple tool changes without manual intervention. This process utilizes a rotating table for additional movement, enabling more complex shapes to be machined in fewer setups. The automatic tool changer switches between tools automatically, reducing downtime and improving production speed. It is ideal for precision tasks requiring different tools, providing both flexibility and accuracy in manufacturing. Clays has been producing high-quality flanges for over 100 years. The process begins with heating steel to 1,200 degrees Celsius in advanced furnaces, creating precise flanges and rings from 400 millimeters to 3,000 millimeters in diameter. These are used in industries like apparatus, machinery, and pipeline construction. Using state-of-the-art butt welding machines ensures perfect welds, followed by processes such as milling, turning, and drilling. CNC machines are used for custom solutions. Rigorous testing, including surface and ultrasonic inspections, guarantees quality. Clays participates in international standardization to meet all requirements. Submerged arc welding is a high-efficiency welding process where an arc is formed between an electrode and the workpiece, with the weld area submerged under a layer of flux to protect it from contamination. Feeding the 75 Tandem mill involves precise material input, ensuring a continuous flow of steel strips through multiple stands, controlled for thickness, width, and surface quality, optimizing production efficiency. Stable cut is a reliable system for manual gas cutting, offering precision and stability. It ensures clean, accurate cuts in various materials, improving efficiency and reducing operator fatigue during cutting tasks. The Jaswant-Singh 4-man rolling mill is a traditional, manually operated system where teamwork and craftsmanship play a crucial role. Typically, 4 skilled workers handle the rolling process. 2 operators manage the entry side, feeding the material, and 2 manage the exit side, receiving and guiding the material. The process starts by heating the metal, if necessary, to achieve the right working temperature. One operator checks the roll gap manually, using feeler gauges or calibrated screws, ensuring it matches the desired thickness. Another worker prepares the metal slab or sheet, carefully aligning it at the entry side. When ready, the material is fed between the working rolls. The operators at the entry side push and guide the metal steadily into the rolls, while those at the exit side pull it through carefully. Communication is constant. Hand signals, short commands, and clear coordination are vital. Each pass reduces the thickness slightly, and after each roll, workers manually adjust the roll gap for the next reduction step. The backup rolls help maintain stability, but the skill of the team is key to getting uniform thickness and avoiding bending or twisting. Workers monitor the material visually and by touch, feeling the surface and checking straightness. Lubricants or coolants are often applied manually during rolling to reduce friction and prevent overheating. In some cases, after several passes, the sheet is reheated if needed, and the rolling continues until the final thickness is achieved. Finally, the workers trim edges manually and inspect the surface quality. Corrections are made immediately if needed, without relying on automatic sensors. Manual rolling demands strength, precision, and a deep understanding of the material's behavior. Every team member must anticipate changes, adjust techniques on the fly, and work in perfect rhythm. A well-trained four-man crew on a Jaswant Singh rolling mill can produce excellent, consistent results, preserving the true spirit of craftsmanship in metal forming. Nordlock wedge locking washers use a unique wedge effect to prevent bolt loosening caused by vibration. The Junker vibration test shows that traditional methods, relying on friction, fail to maintain clamp load. Nordlock ensures stable, secure joints without the need for retightening, offering a reliable, vibration-resistant solution. The production of the new €50 banknote involves a series of complex steps to ensure both security and durability. It begins with the warehousing and stacking of cotton bales, which are then separated and cut into smaller pieces for further processing. The cotton is mixed with water and other ingredients to create paper pulp, which forms the basis for the high-quality banknote paper. Large sheets of paper are created, and a watermark is embedded during this process as an important security feature. Once the paper is finished, it is automatically cut into smaller reels, making it easier to handle during printing. A transparent window is incorporated into the paper using a special technique to ensure its integrity. Hologram striped reels are then applied to the paper, providing an additional security layer that shifts in appearance depending on the angle of the light. After the paper is prepared, it undergoes a thorough visual inspection to detect any defects before being sent to the printing phase. The sheets are automatically packaged to protect them during printing. They are then fed into printing machines, where offset printing is first applied to ensure sharp, clear text and designs. The emerald number is printed using silkscreen printing, creating a color-changing feature visible from different angles for added security. Intaglio printing is then used to create raised ink on the banknotes, providing tactile features that are important for visually impaired individuals. After printing, the banknote sheets go through rigorous quality control checks to ensure that security features like the watermark and holograms are properly aligned. Finally, the printed sheets are automatically cut into individual banknotes and packaged, ready for distribution into circulation. Each step in the process is carefully controlled to prevent counterfeiting, ensuring that the new €50 banknotes remain secure, durable, and easily recognizable.